Hi, everyone. Today we're going to talk about three different topics, all having to do with concentration: molarity, molality, and mole fraction. Molarity should be a review since we talked about it in an earlier unit. Now, if we take a look, molarity is the number of moles of substance divided by the liters of a solution. So we learned earlier that a solution refers to the combination of both solute and solvent together. So when we say liters of solution, we're not simply talking about the water portion for making a solution using the solvent of water, but we're talking about the entire combination of both solute and solvent. So molarity, which is usually represented with a capital M, it's the moles of solute, the substance that's being dissolved, divided by the liters of solution. We use molarity very frequently when we talk about stoichiometry problems involving solutions, when we do acid-base problems, and again, when we're looking at any type of chemical reaction that involves a solution and we're trying to get quantitative data from it. Okay, let's take a look at our next term. So molality, which looks very similar to molarity in terms of its name, is actually different, and it's more than just the single letter. So molality which is represented by kind of a cursive or italicized lowercase m, is equal to the moles of solute divided by the kilograms of just the solvent. We use molality in a lot of freezing point depression and boiling point elevation problems where we're concerned with the amount of solvent that's being used and not, like molarity offers us, the liters of solution. So let's take a look at how we might solve a molality problem. In this case, a solution is prepared by adding 125 grams of sodium chloride into 750 grams of water. So first, I want to remind everyone that our formula for molality is moles of solute, which in this case is going to be our sodium chloride, divided by kilograms of solvent. In this case, our solvent is just water. So let's tackle that first part. We're looking for the moles of solute. We're going to start by taking our 125 grams of sodium chloride and converting that to moles. So 1 mole of sodium chloride, molar mass off the periodic table, 58.44 grams. So in this case, 125 divided by 58.44, we get an answer of 2.1. Looks like we have 4 significant figures, so 2.139 moles of sodium chloride. This is going to be our numerator, so we're going to write this up here. The denominator, remember, is our kilograms of solvent. Well, our solvent is water, and the problem tells us that we have 750 grams of water. Remembering, of course, the number of grams per kilogram, we're going to divide by 1,000. Our denominator is going to be equal to 0.7500 kilograms of solvent. 0.7500 kilograms. And so now when we do our division, 2.139 divided by 0.7500, we get 2.852. This is our answer for molality, but also remember, and sometimes it's more beneficial to write it this way, you can also write this as 2.852 moles of, in this case, NaCl divided by 1 kilogram water. And I stress that because sometimes when we're doing freezing point depression problems or boiling point elevation problems, it actually helps to show the units written out as opposed to just using the abbreviated kind of italicized M. Okay, here's just a little twist on a similar problem. So instead of the problem providing you the kilograms of solvent or even the grams of solvent, this time they're giving you the volume of solvent, and we need to use density in order to convert that into a mass before we can substitute it into our molality equation. So let's take a look at our molality equation first. So just a reminder, we have moles of solid per kilogram solvent. Just like in our previous problem, I'm going to start by taking care of that numerator first and figuring out what my moles of solute is. So in this case, I have 100.0 grams of sucrose, C12H22O11. The molar mass of sucrose off the periodic table is 342.34 grams. H22O11, and that's for every 1 mole of sucrose. So that first part, 100 divided by 342.34, gives me an answer of 0.2921. Now, for the bottom part, so we can write that part up top. The bottom part, you have to find out our kilograms of solvent. Well, in this problem, they tell us that we have 1.50 liters of water. We know that there are 1,000 milliliters in 1 liter. They also tell us the grams of water. They also tell us the density of water, which is 1 gram per 1 milliliter. And finally, we can convert grams, 1,000 of them, into kilograms to get kilograms of water. Now, if we look at this, we are both multiplying and dividing by 1,000. So our number is not going to change. So the 1.50 liters will translate to 1.50 kilograms. Now we can drop in the 1.50 kilograms here. Take our 0.2921 moles divided by our 1.5 liters, and we get 0.1947, or actually 0.195 as our molality. And again, in this case, I'm going to write it in 2 ways, both showing it with just the molal symbol, and then of course, separating that symbol into its 2 components, moles, in this case of sucrose, divided by kilograms of water. Okay, in our third and final measure of concentration, we're going to look at what is called mole fraction. So the mole fraction measures the moles of one substance over the total number of moles of all substances that are present in that sample. So if you look behind me, pretend that this container represents 2 different types of gases. So maybe the red spheres represent oxygen gas and the blue spheres represent hydrogen gas. Together, there is a certain number of moles of each gas present in that mixture. If we wanted to find the mole fraction of hydrogen gas, or the blue spheres, we would count up the total number of blue spheres, convert that number to moles, so assuming that we have a gram amount for it, convert that number to moles. Then we would do the same for the red spheres. Count up the number of red spheres, convert it from grams to mole. Then we would add the two mole amounts together to get the total number of moles. And then we would put the moles of one sample, divide that by the total number of moles. So in this case, the mole fraction for, say, blue spheres would equal the moles of blue spheres divided by the total number of moles. And the moles for the red spheres would equal the moles of red spheres divided by total number of moles. Now, embedded in that is the calculation where you're going to have to figure out how many moles of each type of molecule you have. So let's take a look at how this would work in a problem. So here we have the setup of a simple combustion reaction involving methane and oxygen gas. And they tell us in the problem starting amounts before the reaction occurs for both of those gases. So the very first thing that we're going to want to do is convert each of those gases from grams into moles. Molar mass of methane gas off the periodic table is going to be 16.05 grams of methane. So we wind up getting 12.50 divided by 16.05, which turns out to be 0.7788 moles of CH4. The next part, we're going to do the exact same thing. This time we're going to look at oxygen. So we have 40 grams of oxygen. Remembering, of course, that oxygen is diatomic, so its molar mass is 32 grams. Get 40 divided by 32, or an answer of 1.25 moles of oxygen. Next part. We're going to add those two numbers up to get the total number of moles present. So, total moles is going to equal 0.7788 moles of methane plus the 1.25 moles of oxygen. We get an answer of, looking at decimal places here, so we can only keep two of them. So we get a final answer of 2.03 moles total. So now we want to calculate the mole fraction, basically the percentage, although we don't multiply by 100 at the end, but the percentage of each type of gas in the mixture. So the mole fraction for methane is going to equal the moles of methane, 0.7788, divided by the total number of moles, 2.03 moles total. We wind up in this case with a mole fraction of 0.384. And that number does not contain any units and does not get multiplied by 100 like we would typically do if we were finding a percentage. So it's kind of the decimal percentage for methane and the decimal percentage for oxygen gas. So now to go on to oxygen, we have mole fraction of oxygen, which is going to equal the moles of oxygen, the 1.25, divided by the total number of moles, 2.03. I get mole fraction in this case of 0.616. Again, no unit, and they do not get multiplied by 100 to convert them to a percent. The one thing you'll note is that the mole fraction decimals should add up to give you 1 overall. So since it's a fraction, the different parts that make up this mixture should add together to give us an answer of 1. And they do. Sometimes with rounding, it may be a little off, but you get the point. Okay, that's it for this lesson. We covered molarity, molality, and mole fraction. If you have any questions, please send me a message. Thanks, everyone.